Okay. Hi, everyone. Yeah, I'm Matthew. I'm one of the many new postdocs here in ICC this year, or just the end of last year. My office is 622 if anyone is super excited by my talk or wants to come find me in the future. So yeah, the organisers asked me to talk a little bit about anomalies in flavour physics and the sort of flavour physics work that's going on in ICC. So I'm going to give you kind of a broadish overview to the theory side, because I think especially someone's talking tomorrow about the experimental side as well. So yeah. So to start off, I'm going to explain the two halves of my title. So what is flavour physics? So we'll start kind of a very broad thing, right? So I think we already saw a little bit in the last talk. In the Standard Model, there are this kind of organisation of fundamental particles, and the point is we have kind of three copies of all our quarks and leptons, which are essentially only distinguished by their different masses, plus the fact that because there are three, there are these 3 by 3 kind of matrices, which we call flavour matrices, which have some structure to them. So the different generations we also call different flavours. So these things are 3 by 3 matrices, and these are just sort of a graphical representation of these things that kind of tell you how sort of one generation interacts with the other generation. And so within the Standard Model, the theory, right, says that these things are just essentially random 3 by 3 matrices. They have to be unitary, so there is some small conditions, but they're essentially random, right? There's no prediction for what they should be. There's just kind of four 3 by 3 unitary matrix has 4 input parameters. Those things we just think we have to measure. There's no theory reason it should be anything else. So if you just think of a random 3 by 3 unitary matrix, there's no reason to believe it should have, I guess, any particular structure. And yet, looking at these kind of experimental values, so this one on the left is the so-called CKM matrix, which relates quark flavors. On the right, this is the PMNS matrix, which relates neutrino lepton flavors. And you see, this one definitely, right, this doesn't look like a random matrix. It looks like a kind of almost diagonal matrix with some smaller off-diagonal elements. I mean, similar here, it's kind of, there's this kind of weird square block and a bit here, and it doesn't seem like something that should just come out randomly. I mean, there's no reason it couldn't, but I guess it's not a nice explanation, right? It just happens to look like this. And so I would say the big picture of flow physics is why do the flavors interact in the way they do? Why does this structure or apparent structure seem to come from? Where does it come from? Does it come from anywhere? And so mostly I work on a quark flavor physics, so I'll be talking things about to do with the CKM matrix, and also I think this afternoon there's someone talking about neutrino oscillations, and they'll, I guess, talk more about neutrino flavor side of things. So that's flavor physics. So when people talk about flavor anomalies, what do they mean? So actually, anomalies actually kind of has two different meanings, even in sort of jargon, right, of quantum field theory. So people doing, students doing one of master's courses, or I guess like first year PhD course or something, will often learn about things called gauge anomalies, which is to do with what happens when you quantize theories. And this is not the sort of thing we're talking about. And this often has been known to occasionally lead to confusion in talks where someone is talking about, oh, does this theory have anomalies, and someone else is thinking on a more theory side is thinking on the other thing. But so when people say flavor anomalies, what we mean, what I'm going to mean, is really just a simple thing there where we have measurements that don't agree with the theory predictions. So that's the what I say. If I say I work on flavor anomalies, I mean on predictions that don't agree with the measurements relating to these flavor interactions. Right. So now we're all kind of on the same page of what's going on. What are the measurements we're doing that don't agree with predictions? And that kind of I've given a sort of 4 bullet points of the kind of, I think, perhaps what are some of the main things people are talking about when they're talking about flavor anomalies. So there's this thing called RK, and I'll explain a little bit more in a minute. And this, I think, is perhaps the most common one, where if someone says flavor anomalies, they generally mean something related to RK. And I'll say later this, so the R here, it's to do with ratios, and the K is to do with, it involves K Besons, but this is not, and sometimes it's not massively important, the details. There's also a thing called RD, which again is a ratio, and this time involving D Besons. which is also, I think these two are kind of the center, as it were, of the flavor anomaly world. There's a lot, I think, of interest in bringing in kind of trying to relate other things. And there's also, for example, the G minus 2 of the muon, which, and sometimes it's a very different physics to the other two, because it's really kind of electronic, or it seems like it's a pure electronic thing, just involving muons. But as we'll see, these two things actually involve muons, and so this is why people often think of these together. And finally, there's a kind of a semi kind of a new kid on the block, slightly suspicious, I guess even by anomaly standards, that's often referred to as the kabibu anomaly or the kabibu angle anomaly, or which is even more different. I think it's not super obvious at first how it's related. And this is to do with actually the CKM matrix itself, and I'll get on in a second to these things. I think here, so this is a nice kind of plot, I think, to sort of show that it's not just these things, it's lots of related things. So this is by this Professor Patrick Koppenberg, who's an experimentalist on ICCUB, and he has some nice plots on his website of kind of summary plots, as it were, of all these different observables. And you see, so this is the sort of orange bars are sort of the theory predictions, the blue is the experiment, and you see there's a whole bunch of things where the two don't overlap. And broadly, kind of everything here that's above G minus 2 is all kind of RK related. And I'll say in a second why they're all related. Everything kind of below here is RD and RD related, and also the G minus 2. Because I say people often, sometimes it's nice to try and link all these things together, because it's, as you see here, there's a very big gap here, so it seems like something that needs explaining. Yeah, so okay, so again, we heard a little bit about mesons and baryons in the last talk, and so there's this thing called a B meson, which can decay to a K meson plus leptons, and it can also decay to a K meson, plus electrons. And the kind of, I guess, two most important things about this that you need to know are that, okay, by taking the ratio, a whole bunch of things cancel off, and so it's a super nice thing to do, both as a theorist, doing calculations involving this is super nice, and experimentally also things that you'll otherwise have to deal with cancel off as well. And the kind of, I guess, only really important thing you need to know about this thing is that so I said earlier we have these different flavors of quarks, and this is what's happening on a sort of fundamental level is a B flavor quark turning into an S flavor quark with some leptons coming out, and that's the what's going on. So this is why we have all these related things. These are all sorts of processes where the same B flavor going to S flavor is coming in, and so this is why people look at these. And they're also kind of interested that a whole bunch of things that are related in this way do seem to show something kind of funny going on. Right, so RD, so it's also a ratio. So a lot of stuff cancels off. It's not quite as nice as this RK ratio. For reasons that would take, I think, longer than this talk to really get into and understand, but. Again, so this is a flavor transition. So we have now a B flavor quark going to a C or charm flavor quark. This time it also puts out two leptons, but a charged lepton and a neutrino. And so again, for example, there's lots of processes that involve these kind of these interactions, and just an example of something that's relatively recently done was the lambda B lambda C baryon, which I think is on here at the bottom again, which is related to, and there's several things where the blue and the orange don't overlap. So the G minus 2 is again relatively kind of different, but as I say, it's the same, because we saw this thing, for example, often the end product involves muons. This one, this lepton here could be a muon or an electron, so muons seems like maybe it's going on with muons, and so people often think about there's this thing, the G minus 2 of the muon, which is just that the muon is it's a spin half particle, it has electric charge, and so there's this thing called a G factor, which is a kind of fundamental property, which is kind of classically 2, quantum mechanically close to 2, and so people can calculate and measure how different it is from 2, and it's the two things don't agree. And finally, there's this, let's say, kabibu anomaly, kabibu angle anomaly, which is, I think, quite very much not the obviously related to these other things. But this is the fact that, so as I said right at the beginning, there's these CKM matrices which relate how flavors interact with each other. And the only thing the standard model says about these things is that they have to be unitary. That itself is a restriction, and so it says, for example, if you have a 3x3 matrix, then there are some sum of squared elements should be 1 or 0 or things. There are restrictions on a unitary matrix. And what you can do is do a bunch of kind of independent extractions of the CKM matrix, of the elements of this matrix, and independently test this whether this really works, right? Whether the matrix that we observe is unitary. And people have done this, and generally involves the first generation quarks, the U and the D. And this, well, the U and the D seems to be the measurement that's throwing everything off. And it seems like if you do some of these measurements, the numbers you get out don't correspond to a unitary matrix. Which, as I say, right, the standard model says this absolutely has to be unitary. Our framework says this has to be unitary. So this is another anomaly. But this one, I should say, is actually, it's kind of an interesting one, that the experimental side has not, there's been basically no change there. What happened is some a theory calculation, essentially. There's some theory that you have to do to relate what you actually experimentally measure to the thing we actually want, right, the element of this matrix. And a new calculation, essentially, of how you do this. Someone did a new calculation and said, I think these things that we previously thought were this size were actually a different size. We hairtighted, and it's kind of a very theory-driven thing. So it's kind of different aspect. Yeah. So now I've talked a little bit about the anomalies. I would say why are people excited about these, or why some people not so excited about it? Why are people in this group working on these things? Why is it a big deal or not? So I'm going to start with kind of why people maybe are not so excited. And I think the kabibu angle anomaly is kind of an example of why something that, I mean, I've worked on it a bit, but if I had to put money on it, I would say this is not a thing that's perhaps the most exciting thing happening in flavor physics right now. And as I say, it's essentially that on the theory side, how we relate to experimental measurement to an actual element of this matrix, there are kind of quantum corrections, and people a year or two ago, someone went back and redid some calculation and got quite a different value out of their calculation, which when you plug it in right to get this, seems like something weird's going on. So it's not an experimental thing, but following that, several other people have looked at a whole kind of reevaluated a whole bunch of the different bits that go into this calculation, because it's quite a complex thing. So it's all related to, essentially, I should say, the beta decay, essentially. As there's lots of complicated nuclear interaction stuff going on, that low energy stuff. And I think, silly from what I can tell, I think it's not a clear picture about why what's going on and how certain the people, the experts as it were, in this field are going on. And this is, so I think, why people it's not kind of a nice clear thing. So that's something I think people maybe are personally certainly are less excited about, and it's kind of like that. So the other side of this is why the flavonomics people should get excited about, and I think you can take a view on this from the reasons kind of like this, right? So if you do some experiment, right, and you get some measurement that disagrees with your theory, right, it's the standard model here. But there's some previously known theories. People who have been working on some other theory that says that everyone already kind of knew about, was well known. Right, it says that these things, this is a place you're expecting, where if the standard model is wrong, but this other theory is right, this is where you should see it. And obviously, if you do that, people get very excited, like, oh, this other theory is interesting. Actually, I'll say this, and obviously it's it's nice that maybe it's just this other theory, this thing which should supersede the standard model is, I guess, has more evidence in favour of it. And ideally, right, this new theory tells us something more too. So I said I think the kind of big picture point of flavour physics is we want to understand why there are these flavours, why do they interact in the way they do, and the standard model itself kind of is very agnostic about this. But often theories that go beyond this are not and have some kind of predictions or some reason why the things are the way they are, right? Why the universe has this structure. So that would be a reason to get excited. Another thing, right, is if which I think this is the case really that kind of to a certain extent the flavour anomalies fell into, is that places where no one was really expecting this to be a place where the standard model was wrong, and so there was no big push on a theory side to come up with or theories where this is where I think we should do a measurement because I think my theory disagrees with it. But once you see it, right, once the experiment says, we've measured this thing, we measured RK or whatever, it disagrees with the standard model, without too much effort you can kind of sit and go, here's a fun way we can extend the standard model and write something down. And obviously this is exciting in a very boring sense, right? It's nice and easy to write a paper, everyone can kind of get involved and do some fun, exciting physics and think about what's going beyond. But this is kind of nice. There's also the case where you come up with this new measurement, you say this is good suits my theory, and then everyone has to sit down and think about this for a long time to really come up with some good consistent model where you can predict or post-dict, right, this disagreement, but also agree with everything else and have a consistent theoretical framework. And generally, right, this sort of thing is the idea where what you come out with is quite a kind of complex structure, and it's not too hard to. It's not got lots of dials you can twiddle with. It's kind of it has to be like this or not at all, and therefore it's very relatively easy to falsify, which is obviously super nice from a scientific perspective to be able to say quickly or kind of certainly whether these things work or not. And again, because you've probably had to construct quite a kind of elaborate new structure, whole new extension of the standard model, again, this hopefully and in our case, right, these anomalies are to do with flavour physics, and so you've probably had to put some structure about flavour into your theory, and maybe then this thing is telling you something about how the universe works, how the universe cares about these flavours. Obviously, the personal point is if you can come up with some super nice thing that everyone agrees kind of works and makes some very specific predictions, and you turn out to be right, it's obviously super great for you. So I would, to go back to the actual flavour anomalies, I would kind of classify them in this way, that individually RK or RD are kind of relatively easy to say, okay, there's this one measurement or this handful of measurements that don't agree with the standard model, and I can not too easily add something onto the standard model, and look, it predicts this but not much else. This is super nice. I can write a paper, spend less than a year, do some nice thing. It's a fun thing to work on. But the combination, I think, is a bit harder. I'll say a little bit more about this more specifically in a second. But basically, that you tend to have to build, this more kind of elaborate structure framework around the standard model, on top of the standard model, to explain these things. And therefore, you get these benefits where you hopefully learn something about the universe and flavour, and it predicts something relatively, a whole bunch of different things. Right, so now towards the end of my talk, to really get into the sort of nitty-gritty detail of what we actually think about when we're doing explorations of this sort of thing. So possible things, I think, a thing called a Z prime. So this is a new, a heavy gauge boson, a new vector boson. And generally people put this in by putting in some new, you take the standard model, which is a gauge field theory, you put in some new gauge symmetry, you say there is some new symmetry of the universe. And in some way, because I say, right, it has to do something with, so far it seems like just B quarks, S quarks, muons, you have to, I think, put this in some way, and therefore your new, your symmetry maybe has to do something with flavour that tells you, maybe a little bit at least, gives you some idea of what's going on. There's also these things called leptoquarks. So these are, they're called leptoquarks because they interact with both leptrons and quarks simultaneously. And this is the thing that doesn't happen in the standard model. There are particles that interact just with quarks or just the leptrons, or both, but not at once. You can either do one or the other. And leptoquarks do both, and this is why they're called that. Which is nice in some sense that it suggests, right, that there are some quarks and leptrons. If you have some particle that comes to both simultaneously, they're in some way aspects of the same thing, perhaps. These tend to pop up from sort of big, grand unified theories, which are kind of fun, and I'd say, right, really tell you have some really complicated structure and really tell you something about these things. Scalar leptoquarks are relatively easy to add on. You can kind of just sort of write down a little bit, twiddle some dials, get a nice prediction out, nothing too hard. Whereas vector leptoquarks, which are often quite popular expressions for doing RD and RK, these things at the same time, because they're massive vectors, you tend to need a more serious structure. Basically, you need some new gauge symmetry, but to get this out, it's kind of harder than getting Z prime out. So again, you have to build this whole kind of this whole new framework right on top of the standard model, and that hopefully tells you something. So really, just to finish off, is where are these anomalies going for the future? So this is just a slide from, there was a workshop at the end of last year between the ICCUB experiment and sort of theorists saying, if this thing really is new physics, when do we start saying this really is a brand new thing? When do we start announcing we've discovered something? Right, there was a big deal back when I was still a student, when the Higgs boson was announced, and there was, right, LHC had seen a mass peak, and they'd very clearly seen a thing. And that was announced when we got to this sort of so-called 5 sigma level. But already if you read theory papers on this, you'll see things with 2 sigma, and I think there's, the question is how as a flavor physics community do we think this is going to be real? And also beyond that, how do we convince the world that this is a real bit of new physics, this is really something brand new? And there's quite an interesting discussion. And it's definitely, I think, important to talk about this because I think really, as best I understand the experimental people, over the next sort of 5 years or so, we'll get to a level where this is, I think, really becomes kind of, if everything stays the same, undisputable, both from the LHCb experiment, and also there's a new experiment, Bell 2, that'll come online and can measure exactly these same things. And I think over the next 5 years, maybe less than that, this will be a question of when do flavor physics say, okay, we've done it, we've done some big new thing, when does everyone have to start saying, okay, this is the thing we need to explain, not just flavor physics, but I think probably everyone working in high energy particle physics, when does this go? So I think this is also, as I say, another reason to be excited that relatively near future, I think there'll be ideally there'll be a big announcement and we'll really say this is the thing we've done. And I believe that's the end. Thank you.
Thank you, Matthew. It's time for maybe 1 or 2 quick questions. Okay. Well, maybe you said that, but then I missed it. What would you say is the most exciting of all these anomalies you discussed? Which one is the most exciting from your point of view?
So I'll go to, for example, this like it's decent blot. So the one, this RK thing, as I say, right, so you see here, this is these orange things are the theory with the errors. So if you look at these RKs, there's essentially no theory error. Really, it's a super kind of what we call a super clean observable. There's no argument that the standard model really predicts that this thing should be, it predicts the ratio should be 1, but there's no argument about it. And experiment really seems to say, no, it's not 1. So I think that is, super in that sense, I think it's the best, chance to be able to say, right, a few years to say this is really something new we've discovered. The RD thing is, there's, okay, you can actually see an error bar there, which you couldn't for, say, RK or something. There's a bit more uncertainty. I think there's some arguments about how this works. But this is the one that perhaps is less slightly less likely, but it's the combination of RD and RK would really, I think, or most of the explanations people come up with really, I think, have this big structure and really tell you something about flavor physics. So I think RK is the one I'm excited about because I think it's the most likely to be able to say really surely there's definitely something going on here. But from a science, learning new things about flavor physics, the combination I think is exciting. The muon Gmads 2 is, I mean, this is a huge gap, but is something I've not worked very much on. Don't really understand the theory quite so much. So I guess my personal point of view is RK for chance of saying yes, this is the thing I work on that's on the front page of every newspaper. The RD and RK for really learning something new about the universe.
But these are two sigma anomalies, more or less, right?
Yeah, so RK, so there was a big thing last March when RK just went over 3 sigma on its own. And so all the rest of these things, so the stars are being updated by ICCUB. It's taking large data. So the question is, this is, I mean, kind of the subject of the discussion was, if this on its own is 3 sigma, we expect maybe in another less than 5 years this will go all the way up to 5 sigma. If this on its own is 5 sigma, do we say we found something? If 2 or 3 of these are if this is at 5 and this is at 3 or 4, do we say we found something? But really, the expectation is, I think, over the next few years, I think by 2025 or something, there should be enough data that this will push up to 5 sigma, which was right, was the point when we announced the Higgs, was when we had 5 sigma, and is this when we should announce the Flavour anomalies?
Okay, thank you, Matthew. No one wants to make a question. Okay, so then let's move on. Let's thank Matthew again.